Hey Chem2, this is Dr. Ricardo. We're on the last video, I believe it's number 7 for chapter 16. And we're going to start out with talking about the opposite of acids. We're going to be talking about bases in solution, in particular weak bases. So these are bases that react with water, undergo hydrolysis with water in an equilibrium type of reaction to produce a counter ion of the original base. In this case, it's ammonia is the base, and the counter ion is the ammonium ion plus the hydroxide ion. Okay, so we're going to make the hydroxide ion directly. And in this particular case, if you remember, what makes ammonia a base is the fact that it has a lone pair of electrons on the nitrogen that attract a hydrogen ion over to it, leaving hydroxide by itself. So the way you make hydroxide is you break the water molecule into two parts. Right? So I can show you that pretty quickly. Here's the ammonia. And a lot of our weak bases are going to be ammonia kinds of compounds. Here's a water molecule. So this, just the hydrogen ion, just the H plus part, is going to go on to this lone pair of electrons, leaving behind the hydroxide with the two electrons from here. So I make NH4 positive, that's the ammonium ion, and hydroxide ion. Okay, well, the equilibrium constant for bases are going to be symbolized as capital capital K for equilibrium constant and small b. In this case, like with all equilibrium constants, we take the molar concentration at equilibrium of the reactants. So we have ammonium to the first power times hydroxide to the first power divided by the concentration of the ammonia, the original ammonia at equilibrium. Okay. We leave the water out, just like we always leave water out of the equilibrium. So two things in the numerator, one thing in the denominator, all to the first power, because all the coefficients are 1. Okay? Nothing gets squared. Well, for this very important equilibrium for ammonia reacting with water, and you know what ammonia smells like in water, okay? It smells like Mr. Clean, right? So ammonia and water to make ammonium ion and hydroxide ion, the Kb is very small. It's 1.8 times 10 to the minus fifth. Okay, so we had a lot of Kas with numbers like 10 to the minus fourth, 10 to the minus 5, 10 to the minus 6. That's the way a lot of our Kbs are going to be, small numbers like that, which is good because it's going to allow us to be able to drop the X in almost all of our Kb type reactions. Okay, so if I want to generalize the base, I don't have to think about the individual ammonia itself. I can just call it a base. Okay, in this case, our base is neutral. It doesn't have any charge on it at all. The base is going to react with water, remove a proton from the water to become Hb plus. This is the conjugate acid of the base, and hydroxide. So written here, this is the generalized form of the specific one that we wrote for the ammonia reaction with water. So all of our base equilibrium are going to be hydrolysis reactions, just like the acid equilibrium were. They were the weak acid reacting with water. Here we have the weak base reacting with water to make the conjugate acid of the base plus the ammonium ion. Okay? And again, Hb plus times OH minus divided by B in the denominator. So these two guys in the numerator because they are products. This guy in the denominator because it's a reactant, all to the first power, and we leave water off. So here's an example of calculating what the pH is of a solution of a weak base in water. So our weak base is going to be morphine. So not only morphine is a drug, it also happens to be a base. Okay, it's not the fact that it's a base that makes it have its medicinal properties, or in this case, its pain relief properties. Um, but it's actually the nitrogen that's on here that reminds you very much of the nitrogen that's in ammonia. Okay? So that's what's going to be doing the attracting. So morphine, which is C17H19NO3, we're just going to abbreviate it as MOR, is administered medically to relieve pain. It is a naturally occurring base or alkaloid. What is the pH of a 0.0075 molar solution of morphine at 25 degrees? They give you the Kb. The Kb is 1.6 times 10 to the minus 6, and we're going to do the reaction at 25 degrees like we're going to do all of our reactions. Okay, so we don't have to write out the whole formula for the morphine every time. We can just consider it MOR, or in fact, you could just put B for base. Okay, so we have the MOR, okay, and that's the morphine. It's in its free base form, right? It has no charge on it. It's dissolved in water, and it can react with the water. When it reacts with the water, it removes one proton to become H more plus, right? So it's going to become a cation. Right? You can make the chloride version of this and make a salt and use that, right? So, but here we make the HMOR plus. That's the same thing back here as the HB plus hydroxide ion. So it's a Lewis base because that lone pair of electrons on nitrogen is an electron pair donor, pulls over an H plus, leaving OH minus behind. Okay, so let's do the question. I'm just going to cover up my answers. We're obviously going to have to make a ice table for this, right? They give us the initial concentrations and the Kb. Okay, well, this is a Kb reaction, so we're all set, right? After we come up with this line down here, all of the equilibrium concentrations, what are we going to be able to do? We're just going to plug those numbers back into the Kb and solve it for X. Okay, so what's the original concentration of morphine that they put into the solution? Well, it was given to us in the problem. It's 0.0075. It's a tiny number, right? Which is a little scary because hopefully it's a large enough concentration that we can drop the X. Okay, so we'll see that in a minute. So that's how much I have. Water we don't care about. It's so much. It's never going to play into any of our equations because we leave water out of the equilibrium concentration expression for all aqueous solutions, including the Kb expressions. Do I have any of the protonated version of the morphine at the beginning before the reaction starts? No, that guy's 0. And do I have any hydroxide? No, that guy's 0. Okay, so a couple of things. This number back here, if you wanted to describe it in a unit called millimolar, right? That's 1,000th of a molarity unit. It would be 7.5 because you just bring the decimal place over 3 times. But we're going to do it in molarity, right? All of our ice tables are going to be in molarity. All right, so here we go. How much is this going to change by? Well, let's define X as the amount of morphine that undergoes the reaction. So this guy's going down by X. We don't care about water. This guy's going up by X. And this guy is also going up by X. 0 plus X is X. 0 plus X is X. 0.0075 minus X. So there's my 3 equilibrium values, right? This one is for equilibrium. So those are going to be my important values. Okay, if I leave it like this and plug it into my Kb expression, I only have a teeny tiny problem, and that is I'm going to get a quadratic equation. So let's do the approximation and then look back after and see if it makes sense. Okay, we can only do the approximation by saying that X, when it's subtracted from a number, is going to be small next to that number and insignificant. Now, why can we say that? Because this is 10 to the minus 6th, right? 10 to the minus 6th versus 10 to the minus 3rd. 1, 2, 3. And it's a high number in 10 to the minus 3rd, so it's almost 10 to the minus 2. So it's about between between 3 and 4 orders of magnitude. So what do I mean by that? 3 orders of magnitude is 1,000 times bigger. This number is 1,000 times bigger to almost 10,000 times bigger. So that means x is probably going to be a number that when I subtract it from 0.0075 is going to give me a number that's so close to 0.0075 that I could have easily just approximated this with 0.075. So that's what we're going to do. We're going to use this number. We're going to say the x is small, so it's okay to drop the x. Right? So sometimes people write it like this, and they'll say drop the x. You can do that on the test for me if you want. All right. Well, now, what do I have? I have my KB expression. I'll draw it over here. KB has got to be the HMOR plus times the hydroxide ion concentration, all divided by the equilibrium concentration of the morphine. Okay. Well, I've got those, guys. That's my line down here. So what am I going to do? I'm going to plug X in for this guy, X in for this guy, and my 0.075 here. So I wind up with KB is equal to X times X in the numerator. That's X squared divided by 0.075. So math is pretty easy. And that's what you get there. Okay, so let's finish up. This is top of the next page. This is top of page 21. Okay, if I plug in my value that was given for KB, 1.6 times 10 to the minus 6th over here, then I need to get rid of the 0.0075, so I multiply both sides by 0.0075, so it comes up next to it. And the last step is I'm not interested in what x squared is. So if I bring this up here, I get this times this is equal to x squared. If I want x, I need to take the square root of both of those. So from here to here, just algebra, and then I just have to do the math. So I multiply the two numbers first, and then take the square root. Okay, so if you have your calculator with you, you should go ahead and do that, right? So I have my fancier calculator with me today. So I'm going to go ahead and take advantage of the fact that I should be able to put everything in parentheses. I'm going to take the square root of the whole thing. I'm going to do parentheses, right? So I open my parentheses. Let me stand up a little bit easier for me to see. 1.6 exp to the minus 6th. Okay. Close the parentheses. Right. Times. Well, I should be careful. Let me go back over here and make this guy a double parentheses. This was 1.6 e minus 6, close that guy, times, open parentheses, 0.0075, close the parentheses, close the second parentheses, hit equals. Okay, let's see if I got the same number. I got 1.195, right? 1.095, which rounds to 1.1, which is what I did here in the notes, times 10 to the minus 4th. So that's the value of x. Well, you're not done once you know x. It's not math class. You've got to go back in and say, what was x? So you go back to your previous page and see how you defined x. Well, x, amongst other things, was the hydroxide ion concentration. So if you've got the hydroxide ion concentration, the smartest next step would be to get the pOH, right? So what's the pOH? To get the pH. The definition of pOH is minus the log of the hydroxide ion concentration. So you just have to take negative the log of 1.1 times 10 to the minus 4. So I'm going to do that for you. Okay. So in this calculator, I'm going to put the log first. Okay. I'm going to open parentheses, and I'm going to put 1.1, right? E, where's my E button? E to the minus 4, close the parentheses. Now this number I know is going to come out negative, right? Because the log of a small number like this, 10 to the minus 4th, is going to be negative. So if I get a negative times a negative 3.958, negative times a negative is going to give us a positive, and if I round it off, it's going to give me 3.96. So here's the number from the calculator. Here's my POH, right? I drop the negative sign because my formula has a negative in front of it. Okay, here's the result from the calculator of taking the log of 1.1 times 10 to the minus 4th. And the negative sign goes away because it would be negative times a negative. Okay, well, last step. If the POH is 3.96, that makes the pH 10.14, because we know that pH plus POH is always equal to 14 at 25 degrees, right? So at that temperature, that's the kW for water. Okay, so 14 minus 3.96 is going to give me 10.04. And I'm done. Perfect number of significant digits. These numbers here had 2. This guy here has 2. This is representing the exponent. So when you have a number that's log, the significant digits are going to be the numbers that come after the decimal point. Okay, this is saying that it's 10 to the minus 10th. This is kind of where the power is represented. Okay, so this is a very basic solution because its pH is much greater than 7. Right? Okay. All right. So the next thing that we're going to talk about is really kind of cool, and it's the relationship between the Ka of an acid and the Kb of its conjugate base. So let's take a simple example. Okay, so you could do this with a base and its conjugate acid, or you can do it with an acid and its conjugate base. So the first one that I'm going to do is with a fictitious acid, HA. So this is a weak acid. It's going to be a Bronsted-Lowry acid, meaning it's going to be an acid because it's going to be a proton donor. So what happens is the HA donates 1 proton to water to make hydronium and gives me the conjugate base back, A minus. Okay, so that is a Ka reaction, so we know that. Okay, well, what's a Kb? A Kb is take that conjugate base. If this is a weak acid, then this might have some basic properties. In fact, this acid might be so weak that this guy would be a stronger base than this is a stronger acid. Okay, so if this is a weak acid, that makes its conjugate base also a weak base. So what happens if I hydrolyze A minus? I put A minus into solution. Well, A minus, being a base, can be a proton acceptor, take a H plus from the hydrogen to make the HA back, and hydroxide ion. So you could sort of see this. So here's A minus acting as a Bronsted-Lowry base. It's a proton acceptor. Okay, the water in this case would be acting as the acid. Okay, and those kinds of reactions are called KBs. The only difference between this one and the one we did in the last one is this one is starting out with a negative charge, whereas our last guy started out neutral. Okay. All right. Well, what happens when we add 2 chemical reactions together? If I add 2 chemical reactions together, I just follow all the rules that I would in any mathematical set of reactions. If I add like 4x plus 7 and 3x minus 2, I'm allowed to add those up. So I can do the same thing. Okay? And we know what happens to the equilibrium constants when we add the reactions. We should multiply the equilibrium constants. Okay, so when I add these 2 things, look what happens. Here's A minus that's formed in this one, and then the A minus, though, is used up in this one. So the A minuses would cancel out. Okay, so anything else that cancels out? I've got hydronium and a hydroxide over here. Oh, look, here's my HA. My HA here cancels out with my HA here. Goes in over here, but then it's used up in the next step. So the HAs cancel and the A minus cancels. That means there's only two things left on the left and two things left on the right, these two. Okay, so what's water plus water? Water plus water is two waters. I could write that even simpler. And left on this side, hydronium and hydroxide. Okay, we know the name of this chemical reaction, the autoionization of water, and that's called Kw. So we have just proven that the Ka for an acid multiplied by the Kb for its conjugate base is equal to Kw. If we're doing this at 25 degrees, we know the value of Kw is 1 times 10 to the minus 14th. So that's pretty powerful. Right? All our reactions are going to be at 25 degrees. Ka times Kb is equal to 10 to the minus 14th. So that's an important formula, to know. So if you needed to know the Kb for the conjugate base here, for A minus, you wanted to know how basic is A minus when it gets into solution. So you take some sodium A, right? You put it into solution, it dissolves. When that A minus gets into the water, does it react with the water to make HA and OH minus? Absolutely. And you'll know how strong of a base it is by this. Kb is 10 to the minus 14th divided by Ka. So that's just algebra. To rearrange this, I just bring this A minus underneath. So if I need to know the Kb, I take 10 to the minus 14th and divide it by the Ka. So let's do an example. If I had a Ka that was 10 to the minus 5, which is pretty typical, like 1 times 10 to the minus 5. Okay, so what's this going to be? 10 to the minus 14th divided by 10 to the minus 5, right? How do you do that? You do minus 14 minus a minus is a plus 5. So negative 14 plus 5 is going to give you negative 9. This is going to be 10 to the minus 9. So the Kb for A minus would be 10 to the minus 9. That would be A minus reacting with water to make HA and OH minus. And the Ka for this acid is 10 to the minus 5. The Kb for this base is 10 to the minus 9. So that'll always be the case whenever you have one of these pairs. The strength of the acid times the strength of the base is equal to Kw. Now let's read this last note here. So the pKa of the acid times the pKb of its conjugate base always equals to 10 to the minus 14th at 25 degrees. Okay. Another way to write that is you can take the logs of everything, and I won't do it for you, but you get that the pKa plus the pKb is always equal to the pKw, and the pKw at 25 degrees would be 14. So for our example back here, right, the pKa of our acid HA, if the Ka is 10 to the minus 5, take the log of that, I get minus 5, drop the negative sign, the pKa is 5. The pKb of our base over here with 10 to the minus 9 would be 9, because I take the log of 10 to the minus 9, I get minus 9, and then I drop the negative sign, because whenever I take the p of something, it's minus the log of that number. So this guy comes out to 9. And we know 5 and 9 equals 14, so we've just proven this. So you can do it with the log version. pKa plus pKb is always equal to pKw, which is 14. Or we can do it with the original version, Ka times Kb is Kw, which is 10 to the minus 14. So this is 10 to the minus 14th, this is 14. Good? Okay, let's take a look at an example here. All right. If the Kb of ammonia is 1.8 times 10 to the minus 5 at 25 degrees, what is the Ka of the ammonium ion? Okay, so here's the reaction for Kb, and I'm giving you its value, 1.8 times 10 to the minus 5, and I'm asking you the conjugate acid of ammonia. If it was to hydrolyze, it would give you the ammonia back and protonate this water to make hydronium. So what's its Ka? So the ammonium ion is acidic, right? This is the base hydrolysis of the ammonium ion. Okay, so the Ka is equal to Kw divided by Kb. Where does that come from? Because Ka times Kb is equal to Kw. So I just do a little bit of algebra. Let me get a new piece of paper. I need the Ka for the ammonium ion. Right? Ka for the ammonium ion times the Kb is always equal to Kw. So if I want the Ka of the ammonium ion, the Kb is coming underneath, and I get Kw divided by Kb. Okay. So do the math. 10 to the minus 14th divided by 1.8 times 10 to the minus 5. Okay. If you do that, you get 5.6 times 10 to the minus 10. So if I was going to do this on my calculator, I would put these two guys in parentheses. Put parentheses around here, divided by 1.8 times 10 to the minus 5. The other way you can do it is just take 1 divided by 1.8, get that answer, and then take 10 to the minus 14th divided by 10 to the minus 5, and that one you could do in your head, that would be equal to minus 9. Okay, and then 1 divided by 1.8 is going to come out to 0.156 times 10 to the minus 9th, which would be 5.6 times 10 to the minus 10th. Okay, last note here at the bottom of this page. So we're looking at, these are called hydrolysis reactions. The hydrolysis of an ion is the reaction of an ion with water to produce the conjugate acid and hydroxide, or the conjugate base and hydronium. Okay, so it's the reaction of an ion with water. Here's two examples. Right, this is the one we just looked at. The base, the acid hydrolysis of the ammonium ion. This is the conjugate acid of ammonia, which is NH3. Is the ammonium ion has one too many protons, right? It doesn't look right. It usually ammonia has 3. It's going to donate a proton to water to make ammonia and hydronium ion. Here's an example of a base, right? The acid that's associated with the cyanide ion is HCN, right? Hydrogen cyanate. So this guy would be the acid, and this guy is its conjugate base. The one that we just did, this guy is the acid, and this guy was its conjugate base. This is the natural one, the one that has no charge, acid base, conjugate base of the acid, conjugate acid of the base. So cyanide ion, if you brought it into the solution in the form of sodium cyanide, once the sodium hits the water, it doesn't do anything. It would just dissolve. So the sodium would go off on its own, and the cyanide ion would be left there in water. Well, very quickly it would react with the water molecule, stealing an H plus to make the HCN back and hydroxide ion. Okay, so here's cyanide acting as a base. Okay. If I was going to write the Kb for this, I would just put concentration of this times the concentration of this divided by the concentration of this. If I was writing the Ka for this, it would be this guy times this guy divided by that guy. In both cases, I leave the water out. Okay, that gets us to the last page of the hardest chapter, right? The most in-depth chapter. And that is predicting whether a salt is acidic or basic. So the example we had from the last page was, if I took solid versions of these salts and dissolved them up in water, right? I took sodium cyanide, right? Or I took ammonium chloride. Would these things be acids or bases when they get into solution? Would they make the pH go up, or would they make the pH go down? Okay, so there's going to be 4 rules, okay? So first rule and the fourth one are pretty easy to remember. The 2 in the middle, you have to take a little bit of time and thinking about it. Okay, so rule number 1, the salt that's derived from a strong acid and a strong base is neutral because neither of the ions react with water. So here's an example, KCl, right? K comes from KOH, which is a strong acid. Cl comes from HCl, which is a strong acid. If KOH and HCl were such wonderful acids and bases, KOH is a crazy strong base, right? And HCl is a crazy strong acid. If these guys were great acids and great bases, this is a terrible base, and this is a terrible acid. So the salt that comes from a strong acid and a strong base has a pH very close to 7, because neither of these two ions has any desire to react with water and remove a proton in this case, and um, in this case remove a hydroxide ion to make it an acid. Okay. Okay, here's rule 2 and 3. The salt of a strong acid and a weak base is acidic. So this is going to be opposite. If I take a strong acid and a weak base, it's going to be acidic because the conjugate acid of the weak base will react with water to form hydronium ion. So basically what you have to do is look at the chemical species and see which of the two ions has a tendency to react with water. Okay, so let's go back to our example of, in this case, I need a strong acid and a weak base. Let's do the ammonium ion. Okay, so here's our salt. So when this dissolves in water, I get the ammonium ion, which we've seen has some acidic properties, and I get the chloride ion. So the chloride ion does nothing, right? No tendency to react with water. So I put it with water and just stays chloride. Boring, boring, boring. Nothing happens. Well, if I put the ammonium ion into water, it will react with water by donating a proton to it to give me ammonia back. And if I donate a proton and hydronium, so this guy would be acidic. So this is the conjugate acid of a weak base. So a conjugate acid of a weak base is acidic. This guy's pH would be less than 7 if I put ammonium chloride in. So let's read it again and see if it makes sense. The salt of a strong acid and a weak base is acidic because the conjugate acid, ammonium, of a weak base will react with water to form hydronium. Okay, let's do the other example. This one here. What would happen if I put sodium cyanide into solution? Okay, well, let's read it first. The salt of a weak acid and a strong base is basic. So if the acid is weak and the base is strong, whichever one is strong, it'll be basic for the opposite reason. Okay, because the conjugate base of a weak acid will react with water to form hydroxide ions. Okay, so let's see if we can take our example of NaCN, or in this case I have KCN, and see if it makes sense. Okay, well, potassium cyanide. The potassium in water is going to do nothing with water, right? Because KOH is such a great strong base that it completely reacts. That means K plus has no desire to react with water, so I don't expect anything to happen. But if I put KCN into water, I make the active ingredient the cyanate ion. And how did it react? It reacts with the water that's around it to remove a proton to make the conjugate acid HCN back and OH minus. Right? So if I take an H off of here, that makes it basic. There's my OH, so I'd expect my pH to be greater than 7. This guy would be basic because this is the conjugate base of the weak acid hydrogen cyanide. Okay, so read number 3 again. The salt of a weak acid, that's the HCN, and a strong base, KOH, is basic because the conjugate base of a weak acid will react with water to form hydronium ions. So these are the two that you have that are hard to memorize, number 2 and number 3. Okay, number 4 is, what happens if, well, let's go back to the beginning. Number 1 is, strong with strong is neutral. Here, strong acid, weak base is acidic. Here, flip it. Strong base, weak acid is basic. So you can, if you just want to memorize it, strong basic, strong acid acidic. But it's not for the reason that you think. Okay. What about if they're both weak? Well, if they're both weak, it depends. Okay, so I can't ask you this. So you're like, okay, I don't want to listen anymore. All right. Well, it depends which one of those two ions is a stronger acid or base. So to flip it over, if it's the conjugate of a stronger acid, it's not going to be a good base. They always go opposite to each other. So that one would not be very reactive. If something is the conjugate base to a weak acid, it makes it itself a strong base. So let's take a look at this one. Okay, so the salt of a weak acid and a weak base depends on the relative acid-base strengths of the two ions because they both undergo hydrolysis. Okay, so let's try to talk about this. Here's our example, right? The Ka of the ammonium ion, which we can get from the Kb of its conjugate, ammonia. We already did that, right? The Ka of the ammonium ion is 5.6 times 10 to the minus 10th. I got that by Kw divided by Kb for NH3. Okay. What's this guy? This guy comes from oxalic acid. So this is oxalate ion. Okay. It's not on your group of polyatomic ions that you have to memorize, but it's it's the conjugate. Oops, sorry about that. You guys still going? Good. It's the my screen went out. Sorry about that. It is the conjugate base of HCHO2. So another way that sometimes you'll see oxalic acid written is H2CO. Let me get that right. CO2. Okay, so I remove one of the H's. I'll draw that structure for you too, so you can see it. Okay, so I remove one of the H's and I get its conjugate base. Okay, well, here's the Kb for it. So the Kb for this is 5.9 times 10 to the minus 11. So where would I get that if I couldn't find it on a table? I'd look up the Ka for this guy, look up the Ka for this one, and I can get the and get the Kb for its partner in crime, the one that has one H already gone, right? Because the Kb would be Kw divided by Ka. So usually you're going to find the neutral ones. You're not going to find this on a table. You're going to find this one. You're going to have to calculate this one because it's Kw divided by Ka. So the neutral ones you'll find on a table, you would find this. And between this pair, ammonia and ammonium, you're not going to find the ammonium ion on a table of Kas. You're going to find ammonia on a table of Kbs, and you're going to have to calculate this. In that case, the Ka of the ammonium ion, would be equal to Kw divided by Kb of ammonia. So this is just these two written, flipped over. So just algebra from here to here. Good? Okay. All right. Well, this one would be very close to neutral. Okay. It would be a little bit less because which of these two numbers is bigger? The top one. So this this guy is a little better acid than this one is a base. They're both terrible. 10 to the minus 10th, 10 to the minus 11th. These are not strong acids. So I would expect this thing to have a pH something like maybe like 6.7 or something like that. Okay, so that's the last topic in chapter 6. So we'll see you guys, excuse me, in chapter 16. We'll see you guys in chapter 17.